Welcome back to Calculus 1. I'm Dr. Jeff Groh, and this is your Related Rates Lab. On problem 1, it states, a spherical raindrop evaporates at a rate proportional to its surface area. Show that the radius decreases at a constant rate. Part of the problem here is for you to try to turn a sequence of words into an equation about the rate at which the radius is changing. You need to understand the words and how those can be turned into formulas. A spherical raindrop evaporates. When it evaporates, what is it doing? It's changing volume. Mass is being evaporated off, and you have less and less mass still in the raindrop. So here's the raindrop. It forms, let's suppose, a nice sphere. The material in the raindrop is evaporating away, making smaller and smaller spheres. What is the volume of a sphere? We're losing volume. There's something going on with respect to the rate of change of volume. The volume of a sphere is 4/3 pi r cubed. Now, the problem states that it's evaporating at a rate proportional to its surface area. The rate at which the volume is changing is a negative constant times the surface area. So, what is the surface area formula for a sphere? We need to know the surface area formula too. Well, the surface area formula for a sphere is 4 pi r squared. Many of you probably don't remember these formulas, but you might after today. You can see the rate of change of volume with respect to radius, the derivative with respect to r, is s, 4 pi r squared. Kind of an interesting relationship between the volume of a sphere and its surface area. That relationship is not true for solids and their surface areas in general. It's a special relationship for spheres and certain other geometric objects. We have a negative here because the rate at which volume is changing is negative. The volume should be getting smaller as the raindrop evaporates. Now let's think more directly about this rate of change formula with respect to time. Not radius r, but time. If we take the derivative with respect to time on both sides of the equation for volume, on the right-hand side we need to consider that the radius is a function of time, and so the radius cubed will require the chain rule when we calculate the derivative. So dv dt, when we calculate the derivative, we get 4 pi r squared dr dt. Because we bring the power down, subtract 1 from the exponent, and then we need to multiply by the derivative of r with respect to t, since that's the derivative we're taking with respect to on each side. According to the formula that describes this problem, the rate at which the drop evaporates is proportional to the surface area, and that constant of proportionality should be negative. The surface area being 4 pi r squared. Using all three of these formulas now, we've written down this new equation. The new equation involves the rate at which the radius is changing. Notice that the 4 pi r squareds cancel, and we get the rate at which the radius is changing is minus k. Notice that means the radius changes at a constant rate. Thinking about this principle more generally, if you have a lake with a certain volume, well, how fast that lake evaporates will depend upon how much of that volume is exposed at the surface, how big the surface area is. If it's a broad, shallow lake, there's more surface area from which water can evaporate, and the rate at which you lose volume will be greater. If the lake is very deep and narrow, only a small area exposed on the surface, you won't get very much evaporation from that smaller surface. So the rate at which volume changes with respect to time should, in fact, be proportional to the surface area. It's good form when writing out these constants of proportionality to assume that all physical constants are positive. So if you get a negative number here, you should incorporate that negative by explicitly writing it out front. That way, this constant, the evaporation constant, will be a positive constant. In problem 2, it says, suppose you are standing between a wall and a lamp. You are 5 feet from the wall and 10 feet from the lamp. The wall is 20 feet tall, while the lamp is 10 feet tall. You throw a ball upward, releasing it at a height of 6 feet. So the ball is going this way at a speed of 10 feet per second. How fast is the shadow of the ball moving at this instant? How fast is the shadow of the ball? Here's the shadow of the ball on the wall. As the ball goes up, the shadow should also go up. If the ball is going up at 10 feet per second at this moment, how fast is the shadow climbing up that wall? Suppose we draw in a horizontal at a right angle. This will intersect the wall at 10 feet. Let's define a variable x. We're asking how fast the ball is changing height. We're asking, what is dx dt? So, how do we solve this problem? One way to solve this problem is to drop another altitude, starting from here, and we'll define another variable, y. Let's suppose that dy dt is 10 feet per second. That's what we were told in the statement of the problem. We also have similar triangles, where this distance from here to here is 10 feet. This distance from here to here is going to be 15 feet. Now, this side is going to be 10 minus x, and this side is going to be 10 minus y. Because ratios of corresponding sides of similar triangles are equal, we have the equation 10 minus x divided by 15 is equal to 10 minus y divided by 10. Let's multiply both sides by these denominators. We'll cross multiply so that we will have 100 minus 10x equals 150 minus 15y. Keep in mind that both x and y are functions of time. We can take the derivative on both sides of this equation. We'll get negative 10 dx dt equals negative 15 dy dt, we can cancel a negative from each side and divide by 10 to solve for dx dt, knowing that dy dt is 10. dx dt, which is what we seek then, is 15/10 times 10, which gives you 15 feet per second. On our last problem, the last problem says a person 6 feet tall walks at 3 miles per hour towards a 15-foot tall lamp. How fast is his or her shadow moving? I like this as a good exam type problem. How fast is the shadow moving in particular relative to the lamp? It's best to assign your variables to be related to the things that you're solving for. So I'm going to call this big X and this little x. We have 3 miles per hour is dx dt. What we're trying to find is big dx dt. We have similar triangles, just as in the last problem. So let's see if we can set this up in terms of an equation involving similar triangles that we can take implicit derivatives of. First, we have x, big X divided by 15 is equal to this smaller distance, which is going to be big X minus little x divided by 6. We can now cross multiply 6 big X equals 15 big X minus 15 little x. We'll move some terms around and we'll get 15 little x equals 9 big X. From here we can take the derivative on both sides. We can also divide both sides by 3. We'll get 5 dx dt equals 3 d big X dt. We know that the derivative of little x with respect to time is 3 miles per hour. We deduce then that the derivative of big X with respect to time is 5/3 times 3, and that's 5 miles per hour.